The second part of Chapter 8 is on simple machines. So that's what I'll talk about in this video. So the idea of simple machines, or any machine, but there are simple ones, is that they help you to do work. They don't do work for you. You have to usually put more energy in than you get out, but they make it a lot easier. And we know that work is force times distance. So if you exert a force, call that force N, that's the input force, times the distance you exert that force. We know that's work, force times distance is work. Then that is equal to the force out you get times the distance out you get. And if there is some inefficiencies, what you put in doesn't always come out force times distance, plus there might be energy lost because there's friction and stuff, and so normally they're not 100% efficient. And when you put in some force, you exert a force over a distance, you get out, the machine does some work, force times this distance, and then there's some heat energy lost or something. So that's the idea. Normally you want to put in a small force you move over a big distance equals a big force over a small distance. If you're not strong enough to lift something, but you can exert a small force for a small distance, small force for a big distance, then you can get out a big force, but only over a small distance. An example is like when you use a jack to lift up your car. You can lift up a 2,000-pound car all by yourself, but you exert a small force over a large distance, like you move the jack handle really, really far, and the car barely moves up at all. But at least you can lift it. So you get out a big force over a small distance. So that's the idea. So simple machines help you in a bunch of ways. One of them is they multiply your force. They make you stronger. But the trade-off is distance, right? That means you have to put in a bigger distance, but they make you stronger. You can lift up a car. They can also change the direction of a force, like a pulley. Sometimes it's easier to pull down to lift something up. So you pull down and lift something up. That's another thing that they can do. And you can also use a simple machine to multiply the distance. So here it makes you weaker, but maybe it's not hard to do anyway, and so you exert a big force and you get a small force out, but you get more distance out. So multiply. This also makes you faster. An example, speed is 2e's. An example is like a fishing pole. You move the bottom of the pole a small distance, the top moves a big distance. You don't gain force, you actually lose force, but you gain speed, and it's easy to do anyway, so you don't care about force. So those are three things machines can do. The advantage that a machine gives you is called the mechanical advantage. The ideal mechanical advantage, or the theoretical mechanical advantage, is called either one. I like saying ideal, that's the one I usually see. The ideal mechanical advantage is the advantage that the machine gives you, ideally, if there's no friction. If you want to multiply your force, the ideal mechanical advantage is 1 or greater, so it's greater than or equal to 1. If it's 1, it just changes the direction or something. It doesn't actually multiply your force. If it just changes the direction and doesn't multiply your force, it's equal to 1. Still useful, but you don't get an advantage except the change in direction. If it multiplies your speed, then it makes you weaker but faster, and then the mechanical advantage is less than 1. And the mechanical advantage has no units. Just like mu, it's like the only other thing we're going to have with no units. It just tells you how much stronger a machine makes you, basically. All right, that's the basic idea. So let's look at an example. There are 6 basic simple machines. I think they talk about those in the book. Different devices that help you do different things. Let's look at a pulley, because that's a standard one. So let's say that we have a pulley here, and here's the weight you're trying to lift up, and here's the force you exert. In this case, all the pulley is doing is changing direction. The force, if this is the weight you're lifting, the force you have to exert is equal to mg. So this has an ideal mechanical advantage of 1. Actually, it's probably less than 1 because you got to turn the pulley, and there's probably friction in the pulley. You got to be lifting up some rope. So but still that'd be a 1. It just changes direction. If you actually want some mechanical advantage, then you have to do something like this. You have a moving pulley. You always need a moving pulley. So what you're going to do here is lift up, and we hang our weight from the pulley. So here's our mg. Now, when you lift up, both ropes have to shorten. So if you lift up 1 meter, the pulley only goes up half a meter. So you pull twice the distance, but that means you get twice the force out. So you have to pull up here. Your force is 1/2 the weight. You can lift up something that weighs 100 pounds with only a 50-pound force, but you got to lift it twice as far. You lift it 2 meters, it only goes up 1 meter because you're shortening 2 ropes. The way you tell the mechanical advantage of a pulley system is how many ropes are shortening. Here, no rope is shortening. You're just changing direction. But here, there are 2 ropes that are changing in length as you pull. So, or 2 ropes holding up the weight. That's another way to look at it, right? There's 2 ropes holding it up. This weight is doing half the work, half the effort. You're just holding up one side. Okay, that's a mechanical advantage. This would be a mechanical advantage, ideally, of 2. Actually, the actual mechanical advantage, well, it all depends on how much friction and stuff there is. You have to actually build it and measure it to get that, the actual mechanical advantage. Okay, let's do a 3. This is a tricky one. So if we want a 3, we have to have 2 pulleys now. Let's have one that's hanging there, and one of them one's attached and one is moving, and we're gonna let's see, we'll attach the weight to the moving pulley. Okay, and this pulley has a hook here, and so what you do is you attach the string to the hook, and you wrap it around this one, and you go around the bottom one, and then you have to pull up. Okay, now you can see there are 3 strings that are shortening. 1, 2, 3. You're pulling 1, and this pulley is holding up the other 2. So you're only doing 1/3 the force. So if this thing has a weight of mg, you only have to pull up with 1/3 of mg, 1/3 the force. But if you pull it up 3 meters, it only goes up 1 meter. You're always trading force for distance. You get 3 times less force, but you got to move it 3 times the distance. But hey, at least you can do it, right? So that's an IMA of 3. Ideally, you get 3. Now, actually, it might not be less than 3. Let's say that there's a lot of friction, and the actual mechanical advantage, if you actually do it, you got to pull up with half the weight instead of 1/3. So then the actual mechanical advantage would be only 2, because ideally you pull up with 1/3. But if it's actually, you build this thing and you realize, oh, I actually had to pull up with 1/2 mg, the mechanical advantage would be only 2. It only makes you twice as strong. The efficiency of a machine, the easy way to do it, is it's just the the actual mechanical advantage, which is always going to be equal to or smaller than the ideal mechanical advantage, times 100 to get a percent. So in this case, it'd be 2/3 times 100%, so at 66.7% or something. So that's how efficient it would be. The other way to figure out mechanical advantage, which is, depending on the situation, is more work, can be, but sometimes you don't know the AMAs and IMAs, is the work you get out from the machine divided by the work you put in the machine times 100%. You always get less work out unless it's 100% efficient, right? That work out is going to be a smaller number because some of the work goes into friction. So what actually gets done divided by how much you had to put in times 100%, and that's the basic definition for efficiency. But it works out, if you know the AMA and the IMA, it ends up, you can use that definition also. All right, so those are the basic idea of simple machines. Like I said, there's like 6 basic ones. You can look in the book and they talk about all those. But the idea for the efficiency and everything is the same for any machine. And pulleys are the trickiest ones because you got to count the number of strings and stuff. If you want, one last thing I'll talk about here. Let's say that we wanted a pulley with an IMA of 4. Then all you do is you take your IMA of 2 and you just wrap another rope around it. So let me show you how that works here. So there's our IMA of 2, and let's say we want an IMA of 4, And so then we just go, okay, well, here's our hanging pulley. Okay, so far it's a 2 there. Okay, this would be a 2, but I put a fixed pulley at the top and I wrap it around and go around again, and now I lift up. Now there are 4 strings or 4 ropes holding it up, and so this has an IMA of 4. If I wanted 6, I just get more pulleys, wrap it around again, I get 6, wrap it around again, I get 8. I can keep going and going on forever. I can make as big an IMA as I want as long as you have the pulleys. They're called block and tackles in the real world. Pulley systems, double pulleys and triple pulleys, and you can make it, you can get yourself as strong as you want. If you want an odd number, then you start with the 3 here, and you keep wrapping the rope around. Instead of pulling up, you can wrap it around and go up again, and you get a 5, and then you can go around again, you get a 7. You just keep wrapping the rope around and around again, and you get more and more IMA. If you don't like in this one, you have to pull up. If you don't want to pull up, you can just add another fixed pulley here, wrap it around it, and pull down. That doesn't change your IMA, but it changes the direction. So you mix a fixed pulley like the one above, hang it here, hang it over here, and then wrap it around. It doesn't get you any stronger, but at least then you're pulling down to lift up, which often is a lot easier, right, to go with gravity. You can just hang on it and lift up. So, okay, that is the idea. Hope that makes sense and can help you out with some of the problems we're going to be solving.